I gotta readjust my mirrors. Actually, no, I don't. I'm basically doing the same.
Okay, so what's going to happen is, Augustine, you are going to put your foot on the brake.
Yep.
You know which one that is, right?
Yep.
Which one?
This one. The small one. Every time you get in your car to drive, either to the store, to work, to school, or like me, practicing for your license, little heavy metal fragments are released from your vehicle. 90% of those heavy metals are copper, lead, and zinc. They come from bearing wear, motor oil, tire wear, grease, brake emissions, and other parts. Heavy metals get into the environment through runoff. They then can harm fish by causing higher energy consumption, tissue damage, and even death. Mycelium is what provides nutrients for the fungi. Think of it as the roots of the mushroom, where the mushroom is the fruit. Mycelium can break down organic material by releasing enzymes. This is how it feeds itself. However, this ability can also be used for remediation, and scientists have started using mycelium to reduce pesticides, oil, and radioactive pollution. Similarly, mycelium has been able to reduce copper, lead, and zinc concentrations from water, but not all three with the same mycelium or with high removal efficiencies. The purpose of this experiment is to evaluate the efficacy of Pleurotus ostreatus mycelium in reducing concentrations of copper, lead, and zinc pollutants in a water-based filtration system. My hypothesis is that the mycelium of P. ostreatus will successfully remove significant amounts of copper, lead, and zinc from the water. This experiment had two phases. Phase 1, which used test strips to calculate the concentration of copper, lead, and zinc. Those test strips turned out to be inaccurate, so a second phase was conducted using titration kits to test the concentration of copper and zinc. The materials used for Phase 1 were protective eyewear, an N95 mask, gloves, a scale, 3 North Spore Blue Oyster Grow kits, 8 14-quart plastic bins, 6 small drawstring burlap bags, 250 grams of zinc glycinate and copper gluconate powder, and water test strips. Phase 2 added an aquarium water copper test kit, a Chemetrix vacuum vial zinc test kit, and 24 236 milliliter mason jars. I made my zinc glycinate solutions by mixing 50 grams of zinc glycinate with 4 liters of tap water. The copper gluconate solutions were similarly made by mixing 25 grams of copper gluconate with 4 liters of tap water. In order to make sure I measured the right amount, I would stagger my measurements, first adding a little bit of zinc or copper and testing how much was showing up on my test strips, and adding more if I needed. I measured the zinc and copper outside and upwind in order to prevent breathing them in. I made the 6 mycofilters by cutting the Blue Oyster Grow kits, which consist of P. ostreatus, into 840 gram pieces. I then put these pieces of mycelium into the burlap bags, as you can see here. The mycofilters were then placed into solutions of copper and zinc, 1 filter per bin. This then left 1 copper bin and 1 zinc bin remaining, which I labeled as the control. I would then test the solutions every 3 days for 15 days using the water test strips. For Phase 2, I tested every day for 5 days using new titration test kits. I reduced the amount of zinc glycinate and copper gluconate in the bins. For copper, I found that 0.2 grams would work best for my new testing method. For the zinc bins, I found out that 0.025 grams of zinc glycinate would be the best amount to use after doing some research. Unfortunately, my scale could only measure to the nearest tenth of a gram. This meant I had to use a dilution method in order to get the right amount of zinc glycinate into each bin. First, I measured out 0.1 grams of zinc glycinate and mixed it into 2 liters of tap water. This was my stock. I then filled an empty bin with 3.5 liters of water and added half a liter of stock water to the solution. This gave me 1 bin with 4 liters of water and roughly 0.025 grams of zinc glycinate. I then repeated this 3 more times for the other bins. The test kit I had for zinc would show a color based on the concentration of zinc, but did not come with the tools to measure it. For that, I had to go to the University of Minnesota in order to access a spectrophotometer, which would be able to give me the correct readings for the zinc concentration. Until then, I would collect 25 milliliters of the solution from every trial every day into mason jars. These mason jars were then kept in a fridge to ensure accurate results. The results from Phase 1 showed a 60% decrease in lead in the copper gluconate trials. The lead concentration started at 50 parts per million, and at the end of the experiment was lowered to 20 parts per million. The concentrations of zinc could not be determined in both zinc glycinate and copper gluconate tests. Copper was also inconclusive in all solutions, resulting in Phase 2 being conducted with more accurate means of testing for zinc and copper. In Phase 2, copper concentrations in the copper gluconate solutions went down an average of 33% after 5 days, and zinc concentrations in the zinc glycinate solution went down an average of 87% in just 1 day, reaching levels close to that of water. This experiment supports Pleurotus ostreatus' ability to remove copper, lead, and zinc from water. P. ostreatus had the highest removal percentage of zinc with 87% on average, then lead with 60%, and copper with 33%. My hypothesis is partially supported. Lead and zinc concentrations were significantly reduced. Copper was reduced but has not yet been significantly reduced. This experiment supports P. ostreatus being a low-cost, reliable, and sustainable water filter to be used near roadways. And I hope that soon burlap bags full of mycelium will be placed around highways throughout the world.